Hi, this is Rakesh Naik. We are going to discuss about 01 Knapsack Problem, which is an application of dynamic programming. Before going to start 01 Knapsack, let us try to understand. Let A, B, C and D be 4 boxes and each of them contain some item. Box A contains some item which weighs 5 kg and worth 30 rupees. Box B weighs 3 kg and worth 50 rupees. Box C weighs 6 kg and worth 10 rupees, and box D weighs 1 kg and worth 80 rupees. We are given with a knapsack or bag and we want to put the bags into this box so that it will not exceed 9 kg and will get a maximum profit. So if we'll see this diagram, so if we'll see this table, we can see that item A weighs 5 kg, cost is 30 rupees, so total profit becomes 30 rupees. Similarly, if we want to take box A and box B both, the weight will be 8 kg and the cost will be 80 rupees. If we want to take A and C, the weight becomes 11 kg, which exceeds 9 kg. So it means we cannot take this, it is not possible. If we want to list out, we can find this as a way. We can see that if we choose box A, B and D together, the total weight will be 9 kg and it will have the maximum value of 60 rupees. Let us try to understand this by using dynamic program. Before we start, I request you to kindly take a pen and paper and work out along with me so that you can understand it better. And for better understanding, please see the video till the end. If you are a new viewer for this channel, kindly press the subscribe button so that you will get all my updated videos. So the objective of the problem is, we are given with n objects x1, x2 to xn with weight w1, w2 to wn and with profit p1, p2 to pn respectively. And the capacity of the knapsack is y. If an object I with weight wi is placed in the knapsack, a profit of pi is earned. The objective is to fill the knapsack so that the total profit earned can be maximized. The 01 knapsack problem can be treated as a sequence of decision, and let x1, x2, xn be a 01 vector such that xi equal to 1 if wi is placed in the knapsack for a profit of pi, and xi becomes 0 if we decide not to place the item xi with weight wi. So we cannot pick any fraction of the item, or we cannot pick the same item more than once. That we assume that decision is already made up to wi, and hence the value of x1, x2 to xi minus 1 are known. So let fiy be the corresponding optimal solution when I weights are used and y the remaining capacity of the knapsack. Since it satisfies the principle of optimality, so fiy supposed to be maximum of f of I minus 1 y and f of I minus 1 y minus wi plus pi. To solve the recurrence relation, we have the following assumption with f0y equal to 0. If we assume that there is no weight placed in the knapsack with profit 0, and fiy is minus infinity if y is less than 0. So it can be easily verified that if y1 is less than y2 is less than yk, then f1 y1 will be less than f2 y2 will be less than fk yk. So we will use a ordered pair s to the power I as fi yj comma yj. Here j lies between 1 and k. For each member of s to the power I, we are getting a pair, that is p and w. This part I will say as p. So p and w, so that p is a function fiyj and w is yj. S to the power 0 equal to 0, 0 will take, And to compute s to the power y, we have to first compute s to the power I1, where si1 is a pair pw. S to the power I plus 1 will become s to the power I union si1. Let us try to understand this with the help of an example. Let n equal to 3, as we are assuming there are 3 items available and the weight of the knapsack is 6, with corresponding weights W1, W2, W3 as 2, 3 and 4, and the corresponding profits P1, P2, P3 be 1, 2 and 5. So to initialize s to the power 0 equal to 0 and 0. So we are using this to formula s I1 becomes PW pair and s to the power I equal to si minus 1 union si1. For to start with, we have to find S01. So as we know, it is a PW pair. So the first item, if you want to put, first item profit is 1 and first item weight is W. So P minus 1, W minus 2, this item supposed to be in S to the power 0. It means we can write P minus 1 equal to 0. If we'll solve it, we'll get P equal to 1, and similarly W minus 2, second item of S0, that is 0, becomes W equal to 2. So we got the pair S01 equal to 1 and 2. So we'll find S1. The formula, if we'll use S1 equal to S0 union S01. So already we have initialized S0 to be 0, 0 and we found S01 to be 1 and 2. If we'll take the union, we'll get 1, 2 and 0, 0. Let us try to find S1, 1. Again, it is a PW pair. Item supposed to be in S1. So the second pair is 2 and 3. Profit is 2 and weight is 3. So that's why P minus 2 and W minus 3. This pair supposed to belongs to S1. Now S1 contains 0, 0. So if we'll take the first pair, P minus 2 equal to 0, we'll get P equal to 2, and W minus 3 equal to 0, we'll get W equal to 3. Similarly, the second pair in S1 is 1 and 2. So P minus 2 equal to 1, it will give me P equal to 3, and W minus 3 equal to 2 will give me W equal to 5. I can write it as S11 value to be 2, 3 and 3, 5. Let us try to find S2. S2 equal to S1 union S11. So already we have S1 equal to 0, 0 and 1, 2, and S11 value we got 2, 3 and 3, 5. If we take the union, we will get S2 equal to 0, 0, 1, 2, 2, 3 and 3, 5 pairs. So let us try to find S21. So it is a pair PW where we will take P minus 5 and W minus 4. Why? Because in the last pair, third item's profit is 5 and weight is 4, and it's supposed to belongs to S2. S2 contains 0, 0. So P minus 5, if we'll assign it to be 0, we'll get P equal to 5. W minus 4, then we'll get W equal to 4. Similarly, the second pair 1 and 2, P minus 5 equal to 1, which will indicate P equal to 6, and P minus 4 equal to 2, which will give W equal to 6. The third pair is 2 and 3. Similarly, if we'll proceed, P minus 5 equal to 2, which will give me P equal to 7. P minus 4 equal to 3 will give me W equal to 7. And the last pair 3 and 5, P minus 5 equal to 3 will give me P equal to 8, and W minus 4 equal to 5 will give me W equal to 9. So if I'll write it down, S21 value becomes 5, 4, 6, 6, 7, 7 and 8, 9. Now S3 will become S square union S21. So we are having S21 here and we are having S square written here. So we will get SQ will contain this set. Now we will use the dominance rule. The dominance rule says if we are having a pair called PJWJ and PKWK, and if PJ is less than equal to PK while WJ is greater than equal to WK, then we'll drop the pair PJWJ. What is the meaning of that? It means if we can achieve more profit with less weight, then we'll discard the tuple, those who are having weight more but with less profit. Let's see this. We'll apply dominance rule for S cube. We are having these values. Now see this pair 3 and 5. 3 is the profit and 5 is the weight. If I'll compare with the next pair 5 and 4. So we can earn a profit of 5 with weight 4. It means with less weight I can get more profit. So I have to drop this 3-5 pair. Again you see here 7-7 and 8-9. Because the size of the knapsack is 6, even though I am having higher value, I cannot take it. So S3 will becomes the pair of this 5. Now how would I know that which items I have to take? Now after purging rule is applied, we have to apply the condition, that is if PIWI belongs to S to the power n and PIWI doesn't belongs to Sn minus 1, then I'll take the item Sn, otherwise I'll drop the item Sn. Now our highest value is 6-6. 6-6 belongs to S cube. 6-6 belongs to S cube, you can verify from here, and 6-6 doesn't belongs to S2. So the condition becomes true. So I'll take S3 item. So the third item is entirely placed in the bag. And for the next item pair is for third item the profit is 5 and weight is 4. For the third item, for the next item, I will subtract this 5-4 pair from 6. For the next item, 6-6 minus 5-4 becomes 1 and 2. So I have to check 1 and 2 belongs to S square and 1 and 2 doesn't belongs to S to the power 1. In this case, it is false because 1, 2 also belongs to S1. So we'll not take item X2. But we can see 1, 2 belongs to S to the power 1 and 1, 2 doesn't belongs to S to the power 0, which is true. It means X1 equal to 1. So I can say X1 equal to 1, X2 equal to 0 and X3 equal to 1 with a maximum profit of 6. So the optimal solution is X1 equal to 1, X2 equal to 0, X3 equal to 1 with a maximum profit of 6. Let us see the algorithm of dynamic programming. We have initialized S to the power 0 to be 0, 0 and we have to take one variable I which goes from 1 to n minus 1. So S I minus 1, 1 is a PW pair where P minus Pi and W minus Wi I have to take, and which supposed to belongs to Si minus 1 and W supposed to be less than or equal to Y. I'll do merging and purging for S to the power I minus 1 and Si minus 1 and 1. Now if I get a pair Px and Wx as the last pair in S to the power n minus 1 and Py-Wi is a pair with Pi plus Pn and Wi plus Wn. If Px is greater than Py, then Xn becomes 0, otherwise Xn becomes 1. So like this I will trace back for Xn minus 1 up to X1. We can easily verify that the number of element in S to the power I is equal to twice into the number of element in S to the power I minus 1. If no item got purged, I can say summation of number of element in Si will be summation of 2 to the power n with the summation taken from 0 to n minus 1. So the complexity of 01 knapsack is order of 2 to the power n. Thank you for watching this video till the end. Keep watching, keep learning. Please subscribe my channel. Thank you.